So anyway, let's start. And so this is the first colloquium and this first seminar in this semester. And the speaker is Rina Anno, and I forgot her title, but it's something about A-infinity algebras in DG categories. In monoidal, probably DG categories, if you need an algebra structure. Okay, Rina, please.
Yeah. The way one can have an everyone is of course familiar with the notion of an algebra in a monoidal category. So an algebra object is an object with a map from A tensor A to A, such that a certain diagram commutes. So if you want associative algebra, so A tensor A is to A tensor A. So if we denote the multiplication map from A tensor A to A by mu, or multiplication, then if we go here, mu tensor identity, here identity tensor mu, and it commutes, that's an associative algebra structure. And then one can define modules over an algebra by having, say, A tensor, so by having a map from A tensor M to M in your monoidal category. Also satisfying, having certain diagram commutative. So this today I'm going to talk about how one can introduce an A-infinity algebra object and A-infinity module structure in a monoidal DG category. So first, I would like to explain where this came from, like what do we need it for? So how this idea, or rather the necessity of this construction came about. So I would like to, so we were working, so this is a joint work with Team Logvinenko and Arkhipov, and it came so once upon a time, Tim and I came across a construction, and then Sergey looked at it and said, "Oh, this is Barr-Beck theorem for triangulated categories." So I would like to go Barr-Beck theorem, but actually, rather than recalling Barr-Beck theorem, I would like to compress it a bit and introduce the theorem that we have actually proven. So Barr-Beck theorem for enhanced triangulated categories is a theorem where suppose you have two small DG categories A and B, and you have a functor, so a tensor functor from, so between their respective derived categories, and this functor is tensoring with a bimodule M, so M is an B perfect B perfect bimodule. Then we have the following things. So we have and then this functor has a right adjoint. Right adjoint R from D of B to D of A. And R is tensoring with the right dual to M. So MB is home BMB. So one needs to tweak these definitions a bit to actually to make it derived functors. So so if you just take home, so you have to resolve home MB. So it's derived tensor with MB, or so tensor with the resolution of home MB, or so similar, so a good module quasi-isomorphic to it. But the idea is, yeah, that if so we need M to be perfect in order for there to exist a right adjoint, which is then also a tensor functor. So now we have a monad. We have R and F. So going between D of A and D of B. So we have a functor here. And a functor here. And we can define, so in classical category theory, so if we have a monad, we can then define the Eilenberg-Moore category of objects in the the category which is in this picture, it is D of A. And
Rin, when you say D of A, you mean unbounded derived?
Yes, category? I mean unbounded derived category. So working with perfect modules is its own can of worms. But so for this picture we do need unbounded. So Eilenberg-Moore category is the category of objects in this category, which is, and by this I mean D of A, with the action of the monad RF given just trivially by so Eilenberg-Moore in the classical sense. It's the object in D of A with a map from RF T to T. So satisfying some conditions, and that's a category. And then then the functors F and R factor through this category, and then the Barr-Beck theorem says things about the relationship of this category to D of B, and also in which the situations in which this pair of functors is monadic. Problem with the classical Barr-Beck theorem is that Eilenberg-Moore category is not triangular. So for triangulated exact functors between triangulated categories, Eilenberg-Moore category does not have a triangulated structure. You can't so you can try to define it, but there is no functoriality at some point, which happens with triangulated categories. So we propose an alternative. We define a category that we call RF, just curly RF, and that's actually that's a single piece of notation. That's not a composition of some R and some F. But yeah, so this is essentially the category that is the category of modules over a monad. And we have functors this way that make this commute, and their adjoints that make this commute. And this intermediate category here is essentially the closure of triangulated co-complete hull of the image of A under F. So image of D of A under F.
So just RF, a single symbol, or DRF is also a single.
RF is a single symbol, and essentially this is home B. So bar home. So resolution of home BMM.
So it's a DG category.
It is a DG category.
Okay.
It is a DG category, and it is so it is a it is a fully faithful subcategory in D of B. So the Barr-Beck thing for triangulated Barr-Beck thing for enhanced triangulated categories turns out to be simpler and more straightforward even than the classical Barr-Beck, because we just need this. So we need to test for when DRF coincides with D of B, which means that the adjunction of R and F is monadic, and that for triangulated categories. Being conservative, that some category theory definition, it just means that the kernel is 0. So we just need the kernel of this bold arrow to be 0, which is equivalent to the kernel of R being 0. So this is a DG category statement, but then and as Jan pointed out, this is a statement about unbounded categories. And then we wanted to also explore this for bounded categories, so for categories of perfect modules. And then we needed a better notion of the thing is that this RF itself is an AA bimodule. So it's a DG category, but also an AA bimodule. So this functor is tensoring with RF, over A. And this functor is tensoring over RF with M. And this functor is, because M is M is an AB module, but it's also a module over home MM as well. So, and this tensoring with, over RF MB, and this is tensoring over, the current kernel of this is RF again, but as an RF A module. So this pair of functions is induction and restriction. The problem is that M is B perfect, which makes MB B perfect, which makes MB to be what also perfect. So the almost with this functor, so M is not like if M is A and B perfect, then MB is A perfect, and it preserves compact objects. But M being A and B perfect does not ensure that it is RF perfect. So the bold arrow functor does not preserve compact objects. So this.
So what means RF perfect?
As an RF module.
Oh, okay.
So it's a bimodule, so we can talk about it being perfect as a module on either side. So we needed a better notion here, and we have found it. So the problem is that when we try to define an Eilenberg-Moore category, so in the classical sense, and for a triangulated category, the result is not triangulated. So the proper way seems to be then to define it for a DG category. But when you lift your exact adjunction to DG enhancements, it becomes a homotopy adjunction instead. So now you don't have a pair of adjoint functors, you have a pair of homotopy adjoint functors. So you have, it is possible to lift an adjunction. So if you have again a pair of functors between, so adjoint functors between d of a and d of b, and there then you can have a DG lift there. DG lift to a functor of tensoring with some very nice module M, and tensoring with also nice module MB. This is a homotopy adjunction. And when you have, so you have a so you stop having an actual monad. You start having things up to homotopy, and and at some point we needed a notion of modules, so of an algebra object up to homotopy and modules up to homotopy, and then the way to define it so it yields a reasonable triangulated category that works well with all things is to not have things up to homotopy, but have things up to homotopy, and so lift it to an A infinity structure. So we started with a need to define A infinity modules over a monad. So, and the generality in which that happened was that defined, so A infinity modules, so over an A infinity algebra in a monoidal DG category. So our main point of application is that the category where the algebra lives is a category of DG functors.
So what is a practical example of that?
I mean, this, so the thing I was talking about, so our main
No, it just, you were talking about some abstract construction.
Yeah.
Did you mean
all right,
practical?
I see. So yeah, I'll tell. So maybe I should lead with the main idea to application. So in a monoidal DG category. So the application have in mind is in fact geometric. Out of the way. So application. Suppose you have an algebraic scheme, and suppose you have a affine covering. So it's a disjoint. So then you have yourself a map from a disjoint union of affine spaces, and then take a Cartesian and then F lower star and F upper star are a pair of adjoint functors. So F upper shriek, and you can compare. So this D of so derived category of this, so to derived category of X, and since the derived category of this algebra we are constructing, so it's the triangulated co-complete hull of the image of A, and if this is an affine covering, then the image of F lower star is all of D of X. So we are interpreting D of X as the derived category of some algebra in the category of modules over this, but this is a very nice category. This is in fact this is the derived category of a just straightforward commutative algebra. So the downside to it is that the bimodule M involved. So it's hard to compute this category specifically because F upper shriek is not a nice functor. You are talking about so if UI is spec of QI for some commutative algebra QI, then F upper shriek F lower star is a monad in D of the direct sum of QIs. Problem is that F upper shriek is a derived functor, and it's not a good thing to so hard to write explicitly. But in this specific situation,
can I try to understand? So in this case, so what you intend is on the left-hand side, you have some simpler things, and then you try to reformulate the descent data in the derived category sense.
This is derived descent. Yes.
Okay, thank you.
Yeah. So the thing is that on the triangulated level, this functor is isomorphic to another functor. We can take the Cartesian closure here. Sorry, the Cartesian square, so fiber product of direct, so of disjoint union of UIs and disjoint union of UIs over X. This is a disjoint union of Uij over all Ij, where Uij is the intersection of Ui and Uj. So this is also a spec of a direct sum of commutative algebras. And then pulling back here and pushing forward here is a much nicer thing. And also, so this is RF, and the LF. So LF in this interpretation would be F upper star, F lower star. And if you denote this projection by pi1 and this projection by pi2, then this is isomorphic on the, so as exact functors, so would be a homotopy equivalent between DG. If so, is pi2 lower star, pi1 upper star. And this removes us from X entirely. So this is a thing in terms of QIs. Which
I understand. I do not see where is the infinity in that story. It's pure DG.
Yes. So now it's pure. So A infinity is. So we need to go through A infinity to prove equivalence of categories. So this is a monad. This is a comonad. So modules over, so our point is to prove that modules over the monad are, so category of modules over the monad is equivalent to the category of comodules over the so comonad, and the adjunction is a homotopy adjunction. So I don't know how to prove it without leaving DG.
Well, and also for the derived descent, there are several approaches. So why you think that yours is better? I mean, there are
I don't know yet. Maybe so. We're still finishing this, but I do believe that what we're doing allows us to do things in a fairly convenient way. So without infinity categories and stuff. So mostly the G with a little bit of infinity. So entirely by hand.
Yeah, there are more elementary approaches. Yeah, for example, there is an approach of Kontsevich. I'm not sure how did he polish it, but it's pretty straightforward. Okay, so anyway, go ahead.
Yeah. So that was.
Then I do have a question. So in the descent case, you do need some kind of a cycle condition. So how is the cycle condition reflected in this GG category? Say.
It's, I think it is in, so this, I think it's in the coalgebra. So we are talking here that it's, so like we are proving that it's going to be the derived category of comodules over this coalgebra, and so the coproduct on this coalgebra. So it's probably in the. So if we are talking DG modules, then the condition that something is a DG comodule over this coalgebra is a commutation of some diagram. I believe that's the cocycle condition.
Okay, thank you. Probably your formulate that should be the same.
So yes, so yeah, so classically A infinity structures have been defined on vector spaces. Then you have A infinity algebra is a graded vector space with operations of various degrees and satisfying some relations. And now if we are, so and then in particular the operation M1 makes your vector space in a into a differential complex. But suppose so if you're if you are trying to define an infinity structure on an object, like you have multiplication, so A tensor A to A, then it's associative to up to homotopy, so you are getting a homotopy from A tensor A to A, and so on. But there is there is nowhere to pull the internal differential, so that to pull M1 from. You don't get a degree 1. So by in a DG category, you a priori don't have any natural degree 1 morphism from A to A. So on the category of modules over K, you do, and generally on any category of modules, you do. But if your DG category is not category of modules, then you don't. But it turns out that the equations on MI can be formulated in terms of in DG categories. We just don't have M1, and so all relations involving M1 though can be written in terms of the differential on the terms of DG categories. So we are removing M1 from the picture. We're rewriting MI as equations. So we are rewriting the defining equations by having like so we are going to have Mn from infinity to A times, and we are going to have so dmn. So dmn is something that we substitute for M1 composition Mn, so plus minus Mn composition, well, identity to the I M1 identity to the n minus I minus 1, so rather not here, so this, that you can group the parts that involve M1 together and realize that they're just DMN in a DG category. So we usually define we define the structure of an A infinity algebra in a slightly different way, but I mean it packs exactly the same equation. Let's define it via the Barr construction. So let A be an object in a monoidal DG category. And let MI be maps from A tensor I to A of degree 1 minus I. Of degree, what do we need? 2 minus I. So define a twisted complex. So in the category of, so in the pre-triangulated hull of A, so define a twisted complex that would go, well, define a complex that would go like this. So we have M2 here, we have identity tensor M2 minus M2 tensor identity. We have M3 here. Then here we'll have A, so to the 4. And so this is a sum of, so identity M2 minus identity M2 identity plus M2 identity. I don't have enough space to spell it out on the screen. Yeah, here it will be minus M3. Here, so to A, it will be M4. And so on. So the maps here are going to be sums of identity tensor, so several identities, tensor MI, tensor several identities with certain signs, and the maps that point to A, so the ones that land in the rightmost term of the complex are MIs. And this is an A infinity algebra if this is a twisted complex. So if the equation of the twisted complex so equations that ensure that like derivative of the higher differential is the sum of all two-step combinations between the beginning and the end of this higher differential. Those equations are exactly the equations that define the A infinity structure. Then we can define morphisms as so again, so we have the bar construction of one algebra, we have the bar construction of another algebra, and between them we are going to have a collection of maps that point to B. And F1, F2, F3. And we are going to make it a map between extend this. So having a collection of maps from A to B, we need to extend it to the whole bar construction by certain rules. So this is going to be F1 tensor F1. So dependent on the degree of F1. Now I think yeah, for algebras they're always degree 0. So F1 tensor F1, so F1 cubed here. So and then certain sums. So here the rule is going to be that so it's going to be a sign and then tensor product of several FIs. And then this and then we define composition and differential on those morphisms as composition and differential of maps of twisted complexes. Because we can show that if you compose two maps of this form that whose terms depend in the prescribed form on the components Fi, you get a map of this form. Composition and differential inherited from twisted complexes. And then you can define modules and morphisms of modules in this similar way. And so essentially, so the most general setting is that you have yourselves a by category. So it's DG, monoidal, and also by category, and you have an object here. So you have an object here and another object here. So and the algebra lives in the category of automorphisms, so of endomorphisms of the right object, and the module lives in the category that of morphisms from the left module to the right module. So you don't need an algebra and a module to be in the same monoidal category. You just need the monoidal category where the algebra lives act on the on the category where a module lives. Because as I said, the construction we have in mind is that the algebra is a monad, so it lives in the category of functors, and the module lives in the category. So monad, it lives in the category of and the functors of some category, and the modules are then objects of this category. So, but the interesting thing, of course, is okay. So we made a definition. What can we do?
Can I understand that the category for mixed complexes, say, GG category, this is also monoidal category with a standard tensor product.
Yes.
And then the GG algebra is just an algebra object in the category of mixed complexes. Am I right? Or the monoid?
I don't think so. So like why it is the algebra? So you're saying that the Barr construction of an A-infinity algebra is an algebra object in the pre-triangulated hull of...
Yeah, because of the Barr construction, what you get is a twisted complex.
Yes, but is it an algebra? How do you get the algebra structure?
Well, the question is in the category of twisted complexes. Does that does it have a tensor product structure?
Yes,
So,
twisted complexes do have a tensor product structure, but I don't think it's an algebra object. Like, I don't think that this is an algebra object there. It's just a twisted complex. Yeah. So what? Okay.
And so how then you said the monoid objects. So monoid object in which category? And then you have a monoid, so you have what module one can talk in the category.
Yeah. So if we suppose for simplicity that we have just one monoidal DG category and we have an algebra A, then suppose we have another object of the same monoidal category M, and we have a bunch of maps Pi from M tensor A I to M. Then we are saying that M, so M is a module over A if this, so M tensor A, M tensor A squared, M tensor A cubed. So a complex that we make in the same kind of construction. So this is P2. This is identity tensor P2 minus P2 tensor identity. This is P3. And so if this is a twisted complex. So the structure of the A-infinity module over A is an object and a collection of morphisms from this object tensor power of your algebra to M that satisfy certain equations. And those equations are exactly the equations that make the Barr construction to be a twisted complex.
Okay, thank you.
Yeah, so with modules, it is a bit easier than with algebras because, in particular, these modules form a DG category themselves. So algebras don't, but modules do. So if you can differentiate a morphism of modules and still get another morphism of modules, and Barr construction is a functor from A-infinity modules. Well, I'm going to follow Lefebvre-Hasegawa and call them nodules because there are no unidality conditions. So this would be nodules over A on the right. So node infinity A to the pre-triangulated hull of whatever monoidal DG category they're in. And so that's a functor. So between those two DG categories. And then okay, but this is a definition. What good is it? Turns out that we can prove a lot of the usual things that we have about A-infinity algebras and A-infinity modules. And the most important of them being the homotopy lemma that any morphism of modules whose first component is a quasi-isomorphism is a homotopy equivalence. So the two big results I think we can make so that are really useful. So with this definition is that Well, of course, with so a morphism. So if we have F, bullet is a morphism of modules. So closed degree 0 morphism of modules. And then its first component is then it's a map between underlying objects. And it's a map now in the monoidal DG category we're living in. Now it's not clear what it would mean for F1 to be a quasi-isomorphism. We don't have quasi-isomorphisms in arbitrary monoidal categories, but what is a quasi-isomorphism in the category of complexes of vector spaces is the same thing as a homotopy equivalence. And we argue that the correct notion here is that we want F1 to be homotopy equivalence in A. So anything whose underlying map of first component between objects themselves, so it's a map in A, if it's homotopy equivalence, can be lifted. So like anything that has a first component like this is a homotopy equivalence as A infinity modules.
It's sort of implicit function theorem.
Yes. So I think that the classic proof for usual A infinity modules uses minimal models. So uses cohomology. We don't have cohomology here, but it turns out that yes, like the structure. So we can prove it without using M1, and it's just a very natural thing for these structures to have once you replace. So once you think of F1 as a homotopy equivalence and not as a quasi-isomorphism. And the other thing that we can do with those is transfer of structure. Is that if you have an A infinity module and you have another object of A and a pair of homotopy equivalences between them, you can make the other object an A infinity A module as well, so that it's compatible with those homotopy equivalences. So if E is an A module, and you have a pair of homotopy equivalences in the underlying DG category, then a structure of so you can make F an A infinity module as well, so that you have homotopy, and lift this homotopy equivalence to modules. Then the other thing we can other things we can do require some kind of unitality.
Here the F you are a priori. What is F? E is a module, but F is
I'm using curly A for the underlying monoidal DG category. F is just another object of curly A.
Yeah, and the arrow basically says that E and F are homotopy equivalent, or
homotopy equivalent as objects of curly A.
Okay, I see. Okay.
Then you can make F and A infinity a module as well, and make it so that there are homotopy equivalents. Yeah. Then to get more results, we need to impose some unitality conditions on A and M. And the weakest is homotopy unitality. That would just be that. So yeah, and all the unitality conditions so start with some map from identity to A, where identity is the unit object in the monoidal category. So for homotopy unitality, we just want put A to, so having eta A to A tensor A to A, so to M2 to be homotopic to identity. So it's the most, so the crudest thing that we can possibly do. So the we can also have what we call strong homotopy unitality. Is that so instead of the map A2 from A tensor A to A, it's just map in curly A. We can, so let's make a map mu2 from A tensor A to A. Let it be the map, so we can lift, so we can construct a map as A, so A is a module over itself. So, and we can lift multiplication to a map from A tensor A to A in the category of A infinity modules over A. That would be a map whose components are simply mu I are mi. So mi from an m2 from A tensor A to A, then m3 from A tensor A to A, and so on. So in strong homotopy unitality means that. Yeah, and there are obviously two conditions, so one for eta A and one for A eta. And strong homotopy unitality may require that this is a homotopy equivalence in node infinity A. And then the strongest possible condition of homotopy unitality, in fact, is the condition introduced by sorry, I forgot them all. So that's Fukaya, Ota, Ona, and someone else. I'm sorry about that.
And Doch.
Mm-hmm. Yeah. But so it involves certain relationship, so certain structure, but so in between that we introduce a condition that's we call bimodal homotopy unitality, which I'm not going to describe right now. It is basically a truncated version of full. So, and so it turns out, and basically, so if this, so the unitality conditions say that, so we start with A, we grow an A on one side, then we we target back in via multiplication, and we get a homotopy equivalence. And then the bimodal homotopy unitality, it would be a condition that requires a certain commutativity between, so A and so between, so we can have A tensor A, and then we can grow an A in the middle. And then we can map it to A tensor A in two possible ways. We can go mu2 A, so mu2 identity, or we could go identity mu2. So we can multiply. So this is identity eta identity, and this is mu2 identity, and this is identity mu2. So both these compositions are homotopy equivalences. So strong homotopy unitality implies both these compositions are homotopy equivalences. So consider the two homotopies that make them homotopy equivalences. So the bimodal homotopy unitality is the that those two homotopies are homotopic themselves. So like there is a higher homotopy between them. So it is it is literally a truncation of another kind of infinite homotopies between homotopy structure. So but that's, so we require that for some things, and so let me state the results now. So if A is so, and then yeah, so the stronger unitality, the more of the standard stuff we get. So if A is strong homotopy unital, we get the free forgetful adjunction. Then if A is and if A is bimodal homotopy unital, so the second order truncation of homotopy unitality, then for any module, the three things are equivalent, that E is homotopy unital in a weak sense, just the weakest, most crude sense of homotopy unital, then that, so E is strong homotopy unital, and that E is H unital, meaning that it's homotopy equivalent to its Barr resolution. So its Barr construction is acyclic. And this is essentially what we want to work with categories of modules, because we want to be able to replace, so we want to work, so define a derived category of an infinity algebra as the category of modules that have resolutions. So is H unital means that the Barr construction is acyclic. So yeah, and that's what we, so now we can define the we can define the derived category. So for a let A be a bimodal homotopy unital A infinity algebra, we can define a derived category of A, and so as the homotopy categories, category of homotopy unital A modules. And we can define, so, and its compact subcategory subcategory would be the co-complete triangulated hull of representable objects. So of three modules on representable objects. Of so three of compact objects, I believe. Like this. Yeah. Any questions so far?
My question is, how much time do you need?
I can stop here, or I can talk about coalgebras a bit and module. So because derived categories of comodules for coalgebras is a thing. So
well, you should kind of think how to balance the time of your talk, because maybe there will be questions. So
yeah, I mean, I can stop here. So my question was other questions.
Yeah, okay. So then, are there any questions? Are there any questions?
Why don't you talk about the coalgebras?
Yeah, that's okay, but how much time do you need to explain it, Rina?
I'm not going to go in detail about coalgebras, so probably 15 minutes.
Okay, so you have 15 minutes, just go ahead.
Yeah, so the thing about coalgebras is that the nature, so you define derived categories of modules over algebras. If you try to define derived categories of comodules over coalgebras, so even in the DG setting, the naive definition, like the localization of the category of injective comodules, gives a thing that's most likely not the derived category you want. So Leonid Positselsky is an expert on that, and he wrote a lot about that. And so he defines derived categories of the first and the second kind, and so comodules and contramodules, and it's very complicated. Because so some things that work for algebras, they just fail for coalgebras. So rather than trying to build the theory so what we can do, because we want to work with comodules, we want to restrict the pool of coalgebras. So for certain specific nice coalgebras, we are going to coalgebras for which the same kind of thing works. So for which all is coalgebras for which all the previous results work, and so coalgebras whose for which we can then define the category of derived category, which is going to be where each object is going to have a free resolution. So those and then for which this derived category will be equivalent to the category of modules over adjoint algebra. So these are coalgebras, so that are for these coalgebras, we need, so first of all, how do we define coalgebra? So C is a coalgebra if we have a collection of maps from C tensor, so from C to 2 powers of C now. So we have delta I from C to C to the I. So we have delta 2, we have delta 3. So here we have identity tensor delta 2 minus delta 2 tensor identity, and so on. So the immediate problem with this is that it's not a twisted complex. I mean, so it cannot be a twisted complex in the usual definition because it's unbounded, and it's unbounded to the right. Well, bar resolution was also unbounded, but bar resolution was unbounded, so it was one-sided twisted complex unbounded to the left, which meant that we still had a finite number of arrows coming out of each term. With bar resolution going, so co-bar resolution going to the right, we no longer have that. We have an infinite number of arrows coming out of everything. So we need to redefine the notion of twisted complexes for the unbounded case. And our solution has been that we want, essentially we want the convolution to exist. So we want this collection of arrows still define a map from direct sum to direct sum. And that's less restrictive than requiring all but finite number of arrows to be 0. But we also want to take direct sums either in the category itself, if we are already in the category of modules, or maybe in another category of modules, so whatever. So we want to embed our curly A into some other monoidal DG category curly B, which is going to be the target of taking direct sums. So it could, for example, be A itself, or it could be mod A. So, and this theory has been developed, so in a paper. So this theory and some technical results in the paper with Team Logvinenko, so unbounded twisted complexes. But the biggest drawback, so yeah, and then we can develop all the same things, so taking co-bar constructions. And the biggest drawback of this thing is that the homotopy lemma I mentioned is that so amorphism between modules, so homotopy lemma for modules says that amorphism between modules is a homotopy equivalence of modules if its first component, if and only if its first component is a homotopy equivalence of objects. For co-bar constructions that extend to the right, homotopy lemma, so at least our proof of homotopy lemma does not work. And overall, the homotopy, so so my particular, so my personal belief is that this is exactly the thing that makes derived categories of comodules so unnatural, because I mean the reason A infinity modules work so well is that exactly because every quasi-isomorphism of A infinity modules is a homotopy equivalence. Well, for comodules this is no longer true. So not every quasi-isomorphism is a homotopy equivalence. So we still have a forgetful free adjunction under some circumstances. So we still get the H unitality versus, no, I don't, yeah, we don't get H unitality versus homotopy unitality without homotopy lemma, but so proposed solution is to work with coalgebras. So if C is a, yeah, and then So C is a coalgebra, and A is an algebra, and we propose the notion of homotopy adjunction between C and A, and it's so essentially, so it has a higher units from identity to CIA, and higher co-units from AIC to identity. So, and so some so that satisfy relations, and so and it makes eta 1 and epsilon 1 a homotopy adjunction and curly A, but there are more relations. And then so essentially what it does, it makes identity plus C and an A module C comodule, and it makes identity plus A and C comodule A module. So so A infinity, of course. So in the A infinity sense. And if we have this, and if we have so I think we need C to be homotopy unital and A bimodule homotopy unital. So if we have and the homotopy adjunction, then derived category of C is nice. So then so for these, so for coalgebras with this kind of homotopy right adjoint algebra, we so its derived category of comodules meets the expectations and is equivalent to the derived category of modules over its right adjoint, which is what we want. So we want to be able to jump between the derived category of modules over a monad RF, so with right adjoint to F, and derived category of comodules over the comonad LF, where L is the left adjoint to F. And yeah, we can construct a DG enhancement where so those will be so A infinity algebra and A infinity coalgebra, actually even associative algebra and coalgebra, but homotopy unital. So one thing that we cannot do it completely DG because the enhancements we can work with the break unitality. So we can make it associative and co-associative, but we can't make it strictly unital and co-unital only up to homotopy. But yeah, so the theory works, cogs turn, and we get an equivalence of categories.
So the DC here is just the category of C comodules, right?
Yeah, A infinity C comodules.
A infinity C comodules. Okay.
Yeah, so this is so H0 of H homotopy unital comodules. Yep, so that's it. That's the end.
Thank you. Okay, so official question and answers. Are there any questions?
You said in the coalgebra case that for the complex, that if starting from one point you have infinite many, because on the right hand side arrow direction you have infinite many targets. But once you fix any future targets, and there are still only finite number of arrows.
Yes, but we just need the convolution, so the sum of all the arrows, to still define a map from the direct sum to a direct sum. So if they all are vector spaces, for example, it would mean that for any element of C, for example, so for any vector in C, there are infinitely many arrows that are going out of capital C. But if we pick an element in C, then only finitely many of these arrows are non-zero on this element. This would be enough to define a map to between direct sums.
So you can actually in that case that's a map to the product.
No, if it's finite on every element, then that's a map to direct sum.
Okay. I see. On the
we don't so it's like uniformly, like there is a delta for every epsilon, and not non-uniformly, just there is a delta for every epsilon for every element.
And in the going back to your application for the covering of a scheme, so what's the coalgebra in that case?
So
so the
coalgebra in this case, so in fact, so if we have the thing that the thing that will still need running out is that, so in this example with, so in this example with schemes, where is it? So the exact functors are isomorphic, but we need sorry, that was the wrong one. So this is an isomorphism of exact functors. So their corresponding monads, and by the way, they will both be associative, co-associative coalgebras. So DG lift of both things is going to be co-associative. At least we know how to make the DG lift co-associative. So there is not going to be no problem with infinitely many arrows, because all the hierarchical multiplications are simply zero. Co-associative.
So this actually gives the comonad, right?
Yeah. So we can lift a comonad as in so something that comes from a functor, so from f from a to b, so from tensor multiplication by a module m. We can, so a monad, so composition of a functor and its so comonad, composition of a functor and its left adjoint. We can always lift it to a co-associative but homotopy unital DG coalgebra.
So in this case, the comonad is still living on the category of DG, the derived category of shifts.
Yes. So it will. Okay. So, yeah. So the thing is that it will. So the monoidal DG category is going to be the category of DG functors from modules over direct sum of QIs to itself. So it's a DG category, and modules are going to be objects of the DG category modules over direct sum QIs. Is that the thing is that we need structure of A infinity modules or comodules. So between these DG objects.
Okay, thank you.
Yeah, more questions? I have sort of a perpendicular to what probably to the constructions of your talk. So the A-infinity algebra in the category of the graded vector spaces, it's the same as a non-commutative scheme in this category, endowed with a vector field of degree +1, which satisfies this homological condition that the commutator is itself equal to 0. Now, you can ask for a scheme, I mean, for an upgrade to the world of DG schemes. Yeah, there is this DG algebraic geometry. And so then my question is whether, I mean, whether I'm indeed right, and your infinity algebras in the category, in the DG category, I don't know, like DG category of modules or DG algebra, something.
Yeah, so for example, all of this allows, so your modules can be modules over a commutative ring. So it's, but
yeah, so then do I indeed get this geometric interpretation as a non-commutative DG scheme endowed with this homological vector field?
But a vector field, does it come from M1?
Vector field comes from all
From all of them. So it's the derivation that comes from
it's what you, I mean, it corresponds to the construction I always forgetting, Barr or co-Barr complex.
Yeah, I mean, so
it's equivalent.
Yeah, an A-infinity algebra is so having an A-infinity algebra, you have some DG co-algebra. Yeah, with a what co-derivation.
Yeah, so then kind of intuitively, yeah, I can think just an upgrade of this geometric story to from usual graded schemes to DG schemes. Okay. All right. More questions?
Yeah, I have a question for you. At some point, you said something is an inverse implicit function theorem.
Yeah, but it's standard thing. Yeah, I mean, actually, yeah, it's good that you asked me because I forgot to ask that question. Rina, yeah, I mean, there is a notion of L-infinity algebra, which sort of Lie theoretical version of it corresponds to A-infinity, like Lie algebras correspond to associative algebra. Yeah, but it's purely commutative in the sense that, well, instead of tensor products, you consider symmetric power. Okay,
so symmetric monoidal.
Yeah, but then you should really get DG schemes, not commutative DG schemes, but just conventional DG schemes, endowed with homological vector field. And I recall that Toen, he developed some machinery within his approach to derived algebraic geometry. I'm just curious whether it gives the same notion.
Yeah, I don't know. I haven't looked at that.
Yeah. Okay. Yeah, but so concerning the question of Zhongzhu, I mean, it's sort of, I mean, there is a geometric language for L-infinity or A-infinity algebras, which is very helpful because it helps you to understand what is behind these abstract formulas. At least when you work in the category of the graded vector spaces. I don't know how far, but probably it's useful in general. Yeah, and then indeed you have this M1, which is just a tangent map. And so then you have, it's rather inverse function theorem, but it's a special case of implicit function. Yeah? So that if you have an isomorphism at the level of tangent spaces, then you have indeed a local local isomorphism in an appropriate category. And this is exactly what's going on, because these MIs, they are interpreted as Taylor coefficients of this homological vector field. So M1 is just a morphism of tangent complexes. So then
do you mean Fi's and F1? I think
whatever F1,
I mean,
yeah, F1,
yeah,
not
the
M1, but
the component of the morphism. Yeah,
F1.
Yeah.
Yeah, and then that's then it's exactly implicit or whatever inverse function theorem.
So you mentioned the
It's written in A infinity case. I believe it's written in our paper with Maximov 2006 in archive. It's something notes on, yeah, something like notes on A infinity. Yeah, and for L infinity, I think it's in our book, which will never be finished, but the draft is on my homepage, so you can see it's kind of.
And you also mentioned the tangent complex.
Yes, tangent complex.
And so here in the infinite setting, so how can I see the tangent complex?
It's your infinity, I think it's Barr or cobar, whatever. You take the tensor algebra or coalgebra, depending on your taste. Coalgebra actually is better, but algebra is more geometric. You take tensor algebra, maybe completed. So you of your initial algebra where of this actually shifted by one, but anyway, of your algebra where you want to have your infinity structure. So this tensor algebra should be thought of as, by analogy with symmetric algebra, as certain algebra of functions on the formal neighborhood. Yeah, in the non-commutative. Okay, good. And so these MIs, higher products, they are Taylor components of homological vector field, and M1 is just the first. Okay, so then this A algebra, whatever was the notation, maybe with shifted gradient by one, is your tangent space, but M1 defines a differential on it, so it's a tangent complex.
I see. So M1 defines the tangent complex.
Yeah. Okay, other more questions? If not, thanks again for the interesting talk. And this is it for today.
Oh, it's an interesting organizer for the
Thank
comments.
you. Thank you.